Okay, here's a revision of information based on what you've told me. So here's the data we have for the fire, which we should start with right away. Now there's two ways you can look at a fire actually, and both are valid. You can consider a center point where the fire starts, and you could say the fire starts and then moves outwards like a circle. Not quite accurate because the wind blows in one direction and makes the fire burn, and it depends on the fuel and its path. There's all sorts of factors, but generally speaking, you could make it the fire based on a circle. Well, a circle would be y, which is the area of the circle, is equal to pi r squared, which means this would be the radius of the fire, and the circle would progress, or the fire would progress, much like a parabola, because r squared is the same as x squared, and so our data would be based on the radius increasing day by day. And this works, and is actually logical, but does not fit in with the data they've given us. So we have to reject it, because if I were to plot a graph of a circle, so here in Desmos, Desmos is really nice because I can plot, I'm going to turn off all the other graphs, the exact fire data they gave me. And there's even a way to tell Desmos to fill in these dots. Here they are here. And you can almost immediately see that there is a growth curve going on except for this 3000 dot here. It should be a bit flatter and then jumps up. And one argument you can make for the 3000 is that the kids were playing exactly in a heavily forested area with firecrackers, and that had the most wood in it. And that's why it burst up quickly and then went on a normal growth curve. But right away, if I put in my circle here, let's say I'm making it pi r, I make a normal circle where I have x values, and then the area of y is based on pi times x squared. You can see that circle grows too slowly, so I'd have to multiply it by a ratio. Let's say that's 333. And right away I can see some of my black dots, if I use a circle theory, work quite nicely until you get to the real big numbers. So the real big numbers, which are the more important accurate numbers, imply that there's a faster growth going on. So you could do the analysis and say parabola is close, but doesn't quite fit what's going on, even if I stretch it a bit more. Right? Not bad. You could still come up with useful data from it, but it doesn't quite fit. So clearly we have what could be going on as a growth curve, an exponential curve, and that means each value before it is a exponent of the last one. So here's the data. I'm going to just move this aside. Here's the data again over here. And you can't really use 0 because anything times the 0 is still going to be 0. So the 0 makes it a little bit difficult. So you really have to use day 1 as your basis of growth. And it would grow to some number here and then grow to a number here. But really, these are two pieces of data, and the big numbers matter more because they make the ratio more accurate. And if you look at a normal growth curve, let's look at a normal growth curve, as I've already mentioned. Here's x, and here's x to the, or 2 to the power of x. When x is 0, 2 is 1. When x is 1, 2. When x is 2, 4. And x is 3, 8. And as I already mentioned, if you take this unit and divide it by the last unit, you get 2. If you take this unit and divide it by the last unit, you get 2. If you take this unit and divide it by the last unit, you get 2, which tells you the base of this growth curve. Well, geometric sequences are the same thing. There's a ratio that's getting put to an exponent. So that's the same as our base getting put to an exponent. Geometric sequences follow the same pattern as a growth curve. The problem with geometric sequences is, again, you can really only start with the number 1 because the zeros throw a lot of snags into it. Geometric sequences say this. If I know the sequence, I can look at this number, multiply it times the first number, 3000, multiply that by the ratio, and the exponent over here will be whatever this box is here, minus 1. 4 minus 1, my first term. It only works when the x values go up by 1, which we've done. So it would be 3 to the cubed. And as I said in the other video, we'd therefore have to figure out what 3 to the cubed is equal to 10 and what r is equal to the cube root of 10. And we came up with 2.1, which makes sense. But I didn't realize we had that data. I didn't think we had that data. And those data points are right beside each other, and they're big. So we should actually use those data points. And I'll test it two ways. If I take this and divide it by this last one, I get 3. And the only thing that makes that out of whack is this 1. But again, you can justify that saying the wood burned quickly. What would be this one here, if this one multiplied by 3 to get there? It would be 333.3. And then what would this one be? It wouldn't be 3,000. It would be 1111. This works. This works. And it allows us to predict what we want to know, the day Friday. This is Wednesday. This is Tuesday. This is Monday, Sunday. And we only have the data reported for first day, Saturday, Sunday, no data Monday, 10,000 Tuesday, and 30,000 Wednesday. Well, we can use that ratio as a 3, and we can also see if it fits in the geometric sequence. If we didn't know that, would A4, unit 4, be equal to 3,000 times 3 ratio to the power of, not 4, but 3. Well, that's 9. And 9 times 3 is 27,000. So pretty close. We get 30,000. So it still works if it's a geometric sequence when the first number is 3,000, which is excellent. That's very good. We can even see if we could get 10,000 using that. Will amount 3 equal to the initial amount of 3,000 times the ratio of 3 to the exponent of what unit is that for 3? 3 to the exponent of 2. So it's 9 times 3. And we get a much bigger problem. We get 9 times 3 is 27,000. And actually, I might have done that ratio wrong. 9 times 3,000. Yeah. So we can see that we get a slightly bigger problem. And actually, even that last one is a bigger problem. So you can see that the ratio of 3 doesn't work mostly because the initial value if we use geometric sequencing. However, it does work if that 3,000 is not considered as accurate. And if you consider these to be the accurate numbers. And that's why before I came up with 2.1, which I felt was pretty accurate, but I didn't realize we had a 10,000 unit. So really you should use 3 as a base. Well, let's put 3 to an exponent. And we're going to put 3 to the exponent of 4 and see what we get. Get rid of all that. And why am I doing that? Well, I'm assuming the base is 3, right? And normally 3 to the x would be, actually I have it right here. 3 to the x would produce a 1, 3, do. And this is unit 4, and I produce 81. And up here at unit 4, I produce a 30,000. So the question becomes, how do I turn 84 times what number is equal to 30,000? Well, take 30,000 and divide it by 81. What's 30,000 divided by 81? Let's find out. And why am I doing that? Because I'm trying 370. I'm trying to see what factor goes in front of this 3 to the x, 370, and multiplies it to create these much larger numbers. Because 3 to the x is only going to show the growth in normal numbers. This 81 is represented as 30,000 here. It's being multiplied by something in front to get this 30,000. So let's just see if y is equal to 370 times 3 to the x as a valid result. Now, I would expect to get this answer and not get a good result for that. But let's put it to Desmos. So there's 3 to the x, and there I put y, and let's see what it looks like, and we're going to get rid of the parabola that we had earlier. That almost nails our values. We get the 30,000 almost exactly, and we get the 10,000 almost exactly, and we can even raise that to like 1 to see what we get, or 370.5 to see what we get. Almost exact when it's 370.5 as a moniker for this and that. But look, you see it's the second unit that gives us the poor information, and of course that should be a 0. Now if we really want to, we could multiply it by, let's say, 372, and then just subtract 372 to get that nice 0 in the first box. We wouldn't get an accurate one here, but we get a pretty darn accurate one here and a pretty darn accurate one here. We can even multiply it by a bit more. Let's multiply it by 380 and subtract 380. And why am I doing this? Because at the beginning of the fire we had no fire burning, and then we have 760, and this doesn't match our 3000 data, but this 9880 does beautifully, and so pretty much this is 30,400. So if we do this complete equation, the 380 multipliers to get us our number into 30,000, 10,000, and this minus 380 is to turn that first value into 0 so that it at least looks like our forest fire. And you can see the only data chip that's off the map is this 3000, which could be an outlier. It could be explained as the forest had lots of wood where the fire originated, and then there was less wood as it traveled, which would make sense because urban centers and places where people live have less wood. If there's a river, there's less woods. If it's grass, there's less woods. But this formula here fits quite nicely. And the only reason I slammed a minus 380 in here was to create this nice 0 at the beginning, and that made me increase this multiplier to get my numbers back to normal. But that's just fiddling. So you could say, you know, what number times itself minus itself would get me my 10,000, my 30,000, and my 0. And then it's a pretty good graph. Then I have to look at day 6 to see what will happen on Friday, which is his main question. And I see 276,640 acres are expected to burn on that day. I think he'd be pretty satisfied with this as an analysis. And really the factors that came into play were that these two big numbers are side by side are going to be more accurate than these early numbers. There you go. Hope that helps.